Example 1. Find the global maximum and minimum of f of x equals x cubed minus 9x squared minus 48x plus 52 on the interval -5 to 11. So again, here we have a case where we have endpoints. Our function is restricted to the domain listed here, so we can only consider what's happening between x equals -5 and x equals 11. So we know that we're going to have to use those endpoints, -5 and 11, for our consideration. But we also need the critical points. So remember, we find critical points by finding where the first derivative is equal to 0. So my first derivative here is 3x squared minus 18x minus 48. And I want to know, when does that equal 0? So I'm going to factor this. So first I'm going to pull out a 3. And then I'm going to factor it a little bit further here. So I have two numbers that need to multiply to give me -16 and add up to give me -6. So that'll give me x minus 8, x plus 2. So again, I have three things multiplied together equals 0, and I need to figure out what values will make each of those pieces equal to 0. 3 will never be 0. X equals 8 will make the first parenthesis 0, and x equals -2 will make the second parenthesis 0. So my critical points are 8 and -2. So now at this point, I need to check to make sure that they're in my given interval. So I'm considering x values between -5 and +11. Both of my critical points fall within that interval, so I can use them both. So now what I need to do is I need to test each critical point as well as each endpoint in the original function. So I'm going to take f of -5 and f of 11. So those are my endpoints. And I'm also going to test f of 8 and f of -2. So again, I'm plugging each of these values back into the original function to see the y values that I get from plugging them in, because I know my global max and my global min have to happen at one of these 4 points. So when I plug in a -5 into my original function, I'm going to get -58. When I plug 11 into my original function, I get -234. When I plug in 8 into my original function, I get -396. And when I plug in a -2, I get +104. So these are the values that I'm comparing. And I'm thinking about them on a number line, which one's going to be the highest and which one's going to be the lowest. So here, my global maximum, which I'm going to notate G max, is going to be the highest value on the number line, which is 104. My global minimum is going to be the lowest number on the number line. So that's going to be -396. So I was able to find my global maximum and my global minimum by comparing the values of the original function at my endpoints as well as my critical points. Let's try another one. Example 2. The number h of eggs hatched by a specific insect at a given temperature T in degrees Celsius is given by h of t equals 2t cubed minus 45t squared plus 264t for t between 3 and 15. Find the temperature at which the largest number of eggs hatches. So here, we're looking for the global maximum on the interval 3 to 15. The largest number of eggs indicates that we're looking for a max here. So again, I have endpoints. So I have a restricted domain and my interval is 3 to 15. So I know already that I'm going to be testing 3 and 15 in my function. However, I also need to find any critical points and test those as well. So let's find the first derivative of this function. So my first derivative here is going to be 6t squared minus 90t plus 264. And I want to know, when does that equal 0? So if I factor out a 6, I'm left with t squared minus 15t plus 44 equals 0. And if I factor that one more time here, I'm going to get t minus 11, t minus 4. If you're not comfortable with factoring this way, you are welcome to use the quadratic formula to find the roots. So I have three things multiplied together equals 0. So that means that one of them has to equal 0. So 6 will never equal 0. If t equals 11, my first parenthesis equals 0. And if t equals 4, my second parenthesis equals 0. So I have two critical points here. T equals 11 and t equals 4. So now again, I need to take those critical points and make sure that they're in my interval. So my interval here is 3 to 15. Both of my critical points fall within my interval, so I can use them both for my test. So now again, I want to plug my endpoints and my critical points back into the original function. So my endpoints, I had 3 and I had 15. And then I'm also going to test 11 and 4. So I'm going to plug each of these numbers back into my original function to see what the corresponding y value is, or the number of eggs hatched. So if I plug in a 3, I'm going to get 441 eggs hatched. If I plug in a 15, I'm going to get 585. If I plug in an 11, I get 121. And if I plug in a 4, I'm going to get 464. So here, the global maximum is going to be 585. However, I'm looking for the temperature at which the largest number of eggs was hatched. So I'm actually looking for the independent variable here, the t value, because I want the temperature where this happens. So the 585 happened when the temperature was 15 degrees Celsius. So that's when I got my global maximum at t equals 15. If I had wanted the global minimum, or the smallest number of eggs hatched, I would go to my list and I would see that 121 is my global minimum, and that happens when the temperature is 11 degrees Celsius. So let's try another example here. Example 3. Find the global maximum of the function g of x equals x over x squared plus 1 over the interval x between 0 and 2. So again, I have a restricted interval here. I'm only considering values for x between 0 and 2, and I want to find the global maximum, so the highest value that this function takes on between 0 and 2. So again, I'm going to need to use my endpoints 0 and 2, but I also need to find any critical points. So here, to find my critical points, I'm going to have to do a quotient rule. So my top function is going to be my f, and my bottom function will be my g. Now I need to find each of their respective derivatives, and I can plug that all into the quotient rule to get my first derivative of g. So I'm going to do f prime times g, so 1 times x squared plus 1 minus f times g prime, so x times 2x is 2x squared, all divided by g squared. So remember, critical points happen when your first derivative equals 0 or your first derivative is undefined. So we can consider where this equals 0 by considering where the numerator equals 0, and we can figure out where it's undefined if the denominator equals 0. So let's simplify the numerator a little bit, combining like terms so we can do easier analysis. So we have x squared plus 1 minus 2x squared. So that's going to leave me with 1 minus x squared divided by x squared plus 1 squared. Now, looking at the denominator, x squared plus 1 will never equal 0. There's nothing you can plug into x squared to ever make that 0, so there's no places where this function is undefined. However, if we look at the numerator and we consider where 1 minus x squared equals 0, we can bring the x squared term over and we get 1 equals x squared. So that means x equals plus or minus the square root of 1, which is 1. So x could be 1 or x could be negative 1, and it would satisfy this condition. However, notice that our interval is from x equals 0 to x equals 2. So that means we cannot use x equals negative 1 as a candidate for our global maximum because we're only considering what's happening between 0 and 2. So x equals 1 is the critical point we're going to use to test in our function. So again, we're now going to test the endpoints and the critical points. So g of 0, g of 2, and g of 1. We're going to plug each of those values back into the original function. So if you plug in a 0, you get 0 divided by 1, which is 0. If you plug in a 2, you get 2 over 5, so 2/5. And if you plug in a 1, you get 1 over 2, or 1/2. So looking for a global maximum means we want the largest value. So half is the largest value we get from this list. So our global maximum is 1/2. So that's the global maximum of this function on this interval. Let's look at another example. Example 4. Let g of x be a continuous function that has exactly one critical point and is in the interval -3 to -2. Find the x values at which the global maximum and global minimum occur on this interval, given that the derivative of g at -2 equals 0 and the second derivative of g at -2 equals 3. So here, we have to use the given information to figure out what we know about this function and use that information to determine how we can figure out the global maximum and the global minimum. So here we know that g prime of -2 is 0. So that means that -2 is a critical point of this function because the first derivative is 0 at that point. Now this is important because we were told that this function has exactly one critical point. So that means that we know the place where this happened. That's the only place where the first derivative equals 0. So the only place where we would have a horizontal tangent line on this function. Now we also know that the second derivative of this function at -2 is 3. So we have the second derivative test to classify critical points, and we know exactly what's happening at this critical point. So the second derivative test tells us that if the second derivative is positive at your critical point, that critical point is a local minimum. So here, we know that this function is going to be concave up at -2. So think about what the picture of this function must look like. So at -2, we'll put -2 here. We have this minimum, right? This local minimum. And then we know that we have to be concave up, right? So since we're concave up, we have this sort of bend, which means that if we restrict this graph to what's happening between -3 and -2, that we can easily tell where the global max and global min are going to be based on their x values. So x equals -2 has to be our global minimum because that's going to be the lowest value. It can't turn around and go down further because then we would have another critical point, and we were told there's only one critical point. And that means that x equals -3 has to be our global max because that function has to keep going up to the left. Because again, if it were to turn around, then we'd have another critical point, which we don't. So we're able to discern where our global max and our global min are using what we know about the first and second derivative and local maxes and mins to get a sketch of our graph, and then we can hone in on our interval to determine the global values. Let's take a look at another example. Example 5. Given the graph of f of x below, find the global maximum and minimum for the following intervals. A, x between -1 and +1.5. So here, if we're considering the first interval, that's the entire graph. So the entire graph goes from -1 to +1.5. So if we're looking for the global max and the global min, we're looking for the highest and lowest points on the graph. So the highest point appears to be right here. And the lowest point appears to be right over here. So now I need to find their corresponding y values. So here, this highest point appears to happen at y equals 1.6. So remember, these intervals are counting by 0.2. So we have 1, 1.2, 1.4, 1.6. So I would say here that the global max is 1.6 and the global minimum, if you look here, is going to be at 0. So that happens at y equals 0. Part B, x between 0 and 1. So if we're looking between 0 and 1, that means we're only considering the part of the graph between 0 and 1. So I'm going to trace that in blue so we can see what we're looking at here. So now, if we're considering the global max and the global min on that restricted interval, the global max, the highest point, appears to happen twice at both of the endpoints here. And the global minimum happens to be right about there. So the global max here, or the y value, that's the highest y value, is going to be 1 on this interval, because on this interval it only goes as high as 1. And the global minimum appears to be at 0.8. So it doesn't go up quite as high. And again, these intervals are counting by 0.2. Part C. For the third interval, we're considering what's happening from negative 0.5, which is roughly here, until positive 0.5, which is roughly here. So if we're considering this part of the function, we'll get rid of the rest of it that we're not looking at. Ignore all that other stuff outside of this. We want to find the highest value and the lowest value. So the highest value, again, appears to be at roughly at 1.6. So the maximum here on this interval, the red part you can still see, is about here, which we said was 1.6. The global minimum is the lowest point on this function, so that's actually going to happen around here because it starts to increase, and we said that that happens at roughly 0.8. So again, if you have a restricted interval, you're just looking for the highest and lowest point on that interval, and you're defining it by the y value. Let's look at one more example.